So in this video, I introduced the basic derivative rules, like the constant multiple, sum and difference, product and quotient, and the derivative of the exponential function e to the x, and the power function x to the n. I also go over a couple small examples, and at the end, I introduce higher derivatives. So first, something about notation. If you start with the function y equals f of x, then the derivative, which gives you the slope of the graph and the rate of change of the function, can be written different ways. You can write it as dy dx, you could write it as f prime of x, or you can write it as y prime. And there's others too. These are all the derivative, the result. We need something that says take the derivative in order to symbolically manipulate expressions and also to keep track of where we are as we're doing the act of differentiation. So we'll use the symbol d over dx to say differentiate this function in terms of x. So if you see d over dx, it's a function that works on functions. It returns then the derivative. So it depends upon how you want to write the input. You could write d over dx of f of x or d over dx of y. Either case, when you finish manipulating the object, the end result should be the derivative. Now, you've probably noticed that going and finding the derivative by the definition is no fun. So what we need is some way to go about finding the derivative by using simpler rules. Now, these rules, these derivative rules, there's many of them. In fact, that's what the entire chapter is about pretty much. We're going to introduce only the basic ones today in this video. So the first one, I want to know what is the derivative of any constant function. Well, by definition, the derivative of the function is just this particular limit of a difference quotient. But notice that f of x plus h is c, because it doesn't matter what the input is, the answer is always c. And f of x is c. So the numerator is just c minus c, that's 0. So this winds up being the limit of a constant, which in this case is just 0. We write that this way, that if you ever take the derivative of a constant with respect to x, or in fact any of the variable at all, that is always going to be 0. So let's now take a step up and find the derivative of x in terms of x. So by definition, the derivative of f in terms of x is just the limit of this difference quotient. But f of x plus h is just x plus h because of the function, and f of x is just x. So then if you do that subtraction, the numerator would then be h. So you'd have h divided by h, that's 1. It winds up being a limit of a constant. So the limit is 1. That then says that if you ever take the derivative of x in terms of x, the answer is 1. Notice a neat little side thing. Remember, another way to write the derivative d over dx of x is to put the x up in the numerator. And notice you wind up writing dx divided by dx. It's almost like they cancel to get 1, which is one of the reasons this other notation, not the prime notation, why this other notation, Leibniz notation, is pretty cool. Now, we would like to also know then, what would be the derivative of x to any power? Well, unfortunately, we can't do that. We can't actually explain why the derivative rule is the way it is, because if you go back in your history, look really closely, you'll notice that you never got a definition for x to the n. Oh, you got some definition, a counting definition for x squared, x cubed. You got also a kind of counting definition for x to the 1/3, or x to the 1/2, but you never got a definition for x to the pi. What would that mean? You probably remember that your teachers always said, to evaluate that function, just use your calculator. Well, because we don't actually have a definition, we can't really prove what the result would be. This is going to be one of those, we're going to wait to the very end of the term to come back and figure out why this should be true. I promise you in the end, it just won't be cyclical. The logic will still be fine. So in general, the derivative of x to the n in terms of x is, it's n the power, x the base, and then you reduce the power by 1. That's the answer. Now there's a certain process that we go through in order to find the derivative of an expression. The very first step is to rewrite the expression. Oftentimes the functions do not fit in the rules that we currently have, or we might not have the rules yet, or we want to rewrite the expression in order to explicitly avoid a certain rule. Like we might not like to use the quotient rule, so we do some clever algebra to remove the quotient. Or we don't feel like doing a product rule, so we do some clever algebra to remove the product. This is just an example of doing so. So we're going to rewrite the expression first. We'll then differentiate, and then we'll simplify. The overall goal to rewrite the expression is, if possible, rewrite the expression to become a sum or difference of constant multiples times functions whose rules we know the derivatives of. So for this first one, the derivative of x to the fourth in terms of x, we know that answer. That would be 4 the power, x the base, you reduce the power by 1. Now, the type of power completely doesn't matter. So to find this derivative, it would just be 2/5 the power, x the base. You would then reduce the power by 1. So 2/5 minus 1 is -3/5. But differentiation is more than just rewriting it, which we haven't done yet, and differentiating, which is what I just did. You also simplify. So there's a kind of an unspoken rule that when you take your derivatives, you want to set it up so that it can be used easily later on in the course. And later in the course, we're pretty much always going to be setting our derivatives equal to 0. So we do not want to leave negative exponents. And if we can, if there are any common factors, if there's a sum or a difference, we always take that out and write it as a factored form. So you should write this instead as 2/5 x to 3/5. But if someone asked you, yeah, but what's the answer? They both are. They're both correct. It's just that we kind of prefer the second one rather than the first. This time, I want to know the derivative of the square root of x. Well, to do so, this time I don't have a rule for square root of x. There's no rule for that yet. But I remember that I can rewrite the expression as x to the 1/2. And now I do have a rule for that one. This would then be equal to, it would be 1/2 the power, x the base. I reduced the power by 1. But I wouldn't leave it that way. I'd write it as 1/2 times. I would take the x to the -1/2 power and put it back into the denominator. So the denominator should say x to the 1/2. Except we almost never write that. The reason is because x to the 1/2 is just the square root of x. And it's kind of polite that if you start in a language, you end in the same language. So we kind of leave it that way. For the last one, I have a derivative of a quotient. We don't have a quotient rule yet. We have no way to do that. But that's okay because I can rewrite the expression. And in fact, if the numerator is a constant and the denominator is a monomial, this is always what you should do. To find the derivative, I would write this instead as x to the -3, because then it fits all the other rules you've seen so far. I would write down the power, the base. I would decrease the exponent by 1. And then I'd rewrite it one last time so that I do not have a negative exponent. That's the answer. Now that's just applying the differential operator to an expression. If, on the other hand, you start with function notation, like so, the way I want you to think of it is on both sides, we're going to take the derivative operator and apply it to both sides. Once you've done so, the derivative operator, that is saying take the derivative. If you ever know what it's equivalent to, we replace the derivative operator and what it's applied to with parentheses, and then we fill it with what it's equivalent to. So for example, d over dx of f of x is a fancy way of saying f prime. And we know how to write the cube root of x. That's just x to the 1/3, which allows us to take the derivative as you've seen in my previous examples. That gives you a good foundation on how we're going to be doing these derivatives. Now that we have some basic derivative rules of x to a power of a constant, it'd be nice to know what happens if you add them, subtract them, or take constant multiples of them. So we get these rules. If u and v are differentiable functions of x and c is any constant, then the sum of the functions, the difference of the functions, and the multiple of the functions are all actually differentiable. And in all cases, the derivative of the sum is a sum of derivatives, or the derivative of a constant multiple is a constant multiple of the derivatives. Now these rules are fairly simple, but because the derivative itself is not that simple, it's a limit of a difference quotient, that these derivative rules come out is somewhat surprising. So I'm going to prove at least one of them. Let's look at the sum rule. Let's take the derivative of a sum of two functions. Now that is a limit as h approaches 0 of, you take the function at x plus h minus the function at x. And it's all over h. So if we just take the portion that's inside those brackets and separate those fractions, we notice now that we have a limit of two objects that we know what their limit should be. In this case, the limit of a sum is a sum of limits, and each of those limits is the definition of the derivative of the respective functions. So the derivative of a sum is a sum of derivatives. So let's do an example. At which points will the graph of this function have a horizontal tangent line? Well, if we have a horizontal tangent line, then at that point, for that line, the slope of the horizontal line is 0. But that also means then that the slope of the graph at that point is 0. So that's one fact we get. But then also, we remember that the derivative at the point, in this case just the x-coordinate, would also be the slope. So what we need to do is to first find that derivative, evaluate the derivative of the function. And then second, we're going to solve that the derivative is 0 for x. All right, so first step. Since f of x is 3x cubed minus 9x plus 1, the derivative would then be, applying the derivative operator, you'd get 3x cubed minus 9x plus 1. But the derivative distributes through sums and differences. So you get the derivative operator of 3x cubed minus, well, the derivative operator of 9x plus the derivative operator applied to 1. Now that's going to be the derivative of 3 times x cubed. We take the constant out. And apply the derivative of the rest, minus, we take the constant out, take the derivative of the rest. But the last one here, that's the derivative of a constant. We know what that is. So I put parentheses, and inside I put 0. Now obviously that's silly. Don't write plus parentheses 0. Just don't put the plus at all. But then from here we could then write 3 times. We have the derivative of x cubed, and we have a rule for that. It's 3 the power, x the base, reduced the power by 1. You then have minus 9, the derivative of x, which we have a rule for. It's just 1. So totaling this all up, we then get the derivative is actually just 9x squared minus 9. Moving on to the second step, I would then solve that the derivative is 0. Well, now to do so, that would mean then 9x squared minus 9 equals 0. Clearly those solutions are that x is 1 or negative 1. So the question was, what were the points? I did not give you the points. I give you the x coordinates of those points. So the points would then be 1 comma f of 1 and negative 1 comma f of negative 1. And you could just go back and evaluate those functions to get the full points. So the point would then be 1 comma 3 minus 9 plus 1. That'd be minus 5. So it's 1 comma negative 5. And if you plug in negative 1, you would get negative 3 plus 9 plus 1. That's 7. So the other point's negative 1 comma 7. Now here's a sneaky little trick. It winds up being that quite a number of your previous limits were actually just doing derivatives at single values. So here, if you remember, is another way to write down the derivative at a certain value. Notice that the denominator is a change of x, the numerator is the corresponding changes in outputs, and you're taking the limit as the change of x is going to 0. Because if x goes to x naught, then that denominator is going to 0. So if I wanted to find this limit, you might notice that if you were to come off to the side and say that, what if f of x was equal to x squared? And you would say that x naught is 4. Then you should notice that that limit has the form of, it's actually just the derivative of this function at 4. Since the derivative of this function is just 2x, I can get that limit really quickly. It's just 8. Doing it again, to find the limit of this particular function. This time I have x approaching 0, so it may not be obvious what to do. But this time you can think of it in terms of it's actually the limit as h approaches 0 of, you'd have a 9 plus an h minus 3 all over h. So all I did was change the letter being used in the limit, and I changed the order of 9 and h. If you write it that way, it then has now the form of the limit as h approaches 0 of f of x naught plus h minus f of x naught all over h. All I have to do is identify what is the function and what's the x naught. In this case, the function was the square root of x, and x naught was actually 9. So this limit has to be the same as saying what's the derivative of this function, but at 9. So we've already did the derivative of the square root of x. We found that derivative was 1 over 2 times the square root of x. So the limit is 1 over 2 times the square root of 9, and that is 1/6. That's the answer. So notice a lot of the limits you've been doing actually have been derivatives, just evaluated at a single point. And now that we have a cool way to do derivatives by our derivative rules, we can find those limits actually quite a bit faster. Okay, our last example before we get into more derivative rules. This time I want to find the line that's tangent to the graph, but that line has to also go through the point that you see. Now the problem is that this point is not a point in the graph, so I can't use that point in order to find the slope. So we'll have to do this in a slightly different manner. I don't know what the point of tangency is. Here it is. We'll just guess. We'll say that point's right here. Now that point has an unknown x coordinate. I'll call it A. That would then mean, though, that since that point's on the graph, well, then I know what the slope would be. I know what the y coordinate would be. It'd be 1 over A. Now the point that I have over here is the point 0, 2. So through this point and the point of tangency, I have a slope. That slope is found by just taking the difference in the y coordinates all over the difference in the x coordinates. That's the slope of that line. So it's the slope in terms of this unknown x coordinate. But we also remember that the slope is the same as the derivative evaluated at the point. In this case, the only thing you need to get the point is the x coordinate, because the y coordinate is determined by the x coordinate. So I just need the derivative. Well, but if f of x is equal to 1 over x, that's the same as x to the negative 1. So then the derivative is found by just taking the derivative operator and applying it to x to the negative 1. And that would then be negative 1 the power, x the base. You reduce the power by 1. So that is negative 1 over x squared. So the slope is also negative 1 over a squared. Well, but they have to be the same slope. So these things are equal to each other. So I have 1 over a minus 2 over a has got to equal negative 1 over a squared. Let's just multiply everything by a squared. If you do so, you would get a times 1 over a minus 2 would have to equal negative 1. Just multiplying that out, that would then give you 1 minus 2 times a. That would then be negative 1. That means negative 2a equals negative 2. That means a must have been 1. So we now know the point of tangency. Well, now that we know the point of tangency, I also know the slope. I also know the y. I also know the whole point. So the point was actually the point that was 1, 1. That's our point. And the slope is, it was negative 1. All you have to do is evaluate the derivative where a is 1. So the equation of the line then is, just kind of trying to find some space to write it down, you'd write y minus the y coordinate is equal to the slope times x minus the x coordinate. And feel free to go ahead and simplify that to get an equation y equals if you want to. Notice in this problem, In order to find the derivative, I couldn't use the point they gave me because that's not a point on the graph. All right, in order to do more things, we need more derivative rules. So let's get another base rule. The derivative of e to the x. Well, by the limit process, I would take the limit of e to the x plus h minus e to the x over h. That, though, there's actually a common factor of e to the x, because you can rewrite the e to the x plus h as e to the x times e to the h. But that would then mean in the limit, e to the x is a constant, because h is what's changing. So I really just need to know what's the limit of e to the h minus 1 over h as h goes to 0. Well, if you look at the graph of e to the h, or in this case just e to the x, you could then guess by looking at the graph and coming from the left and the right that it appears that the limit should be 1. Problem is, though, that's a guess. You should remember that graphs are not, unfortunately, very safe. It's just a visual depiction of what might happen. If we zoomed in more, maybe bad things happen. We don't know. So this is going to be one of those, again, eventually we can prove it. Eventually we'll be able to prove that the derivative of e to the x is in fact e to the x. It's one of those, we don't know what exponentiation means. E to the pi, we don't have a definition for that. So we can't do any kind of argument based upon an object whose definition we don't know. So for now, the derivative of e to the x in terms of x is e to the x, and we'll come back y later. So let's go do the last derivative rule for the day. If u and v are differentiable, then actually their product is also. But sadly, the derivative of a product is not a product of derivatives. It's a summation of products, and each product actually has only one derivative in it. But if the function v is non-zero, then the quotient u over v is also differentiable, and the derivative of a quotient is not the quotient of derivatives. It's something else. The denominator is being squared. The numerator is a difference of products, and in every product you have only one derivative. These rules are things that if we can, we avoid. If we can rewrite an expression so there's not a product or not a quotient, we often just say, the hell with it, let's just do it. There's sometimes when we don't, so we need to know them both, but there's plenty of instances where we do our very best to avoid these rules. In particular, the quotient rule is one that people forget all the time. The order here matters a lot because of subtraction. So people remember this. The derivative d of the high part and the low part is equal to, you take the low d high, so it's the low factor times the derivative of the high, minus the high factor times the derivative of the low. So it's low d high minus high d low. And that's all over the low squared. You can also do this something similar to the derivative of a product, because a product is a first factor and a second factor. So then it's the derivative of that thing would be, it's the first factor times the derivative of the second factor plus the second factor times the derivative of the first. This way the derivative is always last in every product. This is often what I will say, although for the derivative of a quotient, I almost never do this low d high thing. I just say numerator and denominator because that's what they are. But if it's easier to say low d high for you, please use it. As long as you get the answer right, that's what matters. So the product rule and the quotient rule, the results are not what you would expect. You would expect the derivative of a product is a product of derivative because it's kind of what you've been trained to think. But since that's not true, we really do need to justify it. Otherwise, if we always just keep going on with life and saying, don't worry about it, don't worry about it, you know what, at some point you're going to worry about it. So let's just start laying down that foundation of just basic mathematical literacy so that later on, if I ever do this again, you're prepared for it. Don't worry, you never have to do this yourself. I'm just hoping that you can follow along with what I'm doing. So, the derivative of the product will then equal the limit as h approaches 0 of evaluate the function at x plus h. Then subtract the function, and that's all over h. Now, to do something kind of clever, in the numerator, I'm going to add and subtract the same thing. Essentially adding 0, just a funky way. Here I am And you can see right in the middle, I am adding 0. I did that because I want to manipulate what you see to be a bunch of fractions where some of them I know how to take the limits of. So you can rewrite that entire fraction this way by tearing it apart. It's the same as the limit of this particular sum of products. Take a second to look at it, pause it if you want to verify that it algebraically is fine. Just add the fractions back up. You'll get what I had in the beginning. But the limit of a sum is a sum of limits. The limit of a product is a product of limits. So let's take the limit of each of these pieces separately. Well, the limit of the first factor of u of x plus h, that would just be u of x. And you think of it as because I plugged in 0 for h. But it's actually a little more subtle than that. I never said that u was continuous. Except I did imply it because I said u was differentiable, remember? And that means that u is continuous. So I'm allowed to plug that 0 in for h. The limit of this next fraction, that's the definition of the derivative of v. So we have that one. Then you have the limit of a constant, because v of x does not have h in it. So x is the constant, so v of x is the constant. So that limit is just v of x. And the limit of the last fraction is just the definition of the derivative of u. So that can give us our final result. Let's do an example. I want to know what is the rate of change of the function x cubed times e to the x. Now rate of change, all that is just find the derivative. So then the rate of change depends upon what x value you give it. So we should get a function of x when we're done. So I need to know then what's the derivative of this function f. Well, that would then be I apply the differential operator, or the derivative operator, to x cubed times e to the x. Now if I had a chance, if I had a way to just do that multiplication and avoid this product rule, I would probably just do it, but you can't simplify that. So we write down the first factor, the derivative of the second factor in that product, plus the second factor in that product times the derivative of the first factor. I can then go back and simplify that. That's an x cubed. But we know that the derivative of e to the x in terms of x is e to the x. So I put parentheses first and put the answer inside, plus e to the x. But we know the derivative of x cubed. That's just put in parentheses first. It's 3 to the power, x to the base. You then reduce the power by 1. That then tells you that the derivative is equal to, just making each product look nicer, be x cubed e to the x plus, put the constant first, the monomial next, then e to the x. That's the derivative. But you know what? Remember how there's 3 steps to do a derivative? Rewriting, which I didn't do this time. Differentiating, which was all of this. And then simplifying? Well, I'm not actually done simplifying, because if I can, I'm going to pull out common factors. There's a common factor of x squared and e to the x. What would be left behind is an x plus 3. My final answer then I would write as x squared times x plus 3, monomial, binomial, then the exponential. That's it. That would be the derivative. This has been very, very easy to set that equal to 0 and to solve for x. So let's differentiate this function in terms of t. Now when you do so, you do not write d over dx. That means take the derivative in terms of a changing x. There is no x here to change. So we'll take the derivative in terms of t. That means on the left-hand side, you could write y prime. Or if you want to be more explicit, you can write dy dt. So I then apply the derivative operator here to 3t squared minus 1 all over t squared plus 5. And if there was any way to rewrite that quotient, I definitely would, but there's not really any way to do it. So here, to do this derivative, I'll just apply the quotient rule. That would then be big long bar, because we're going to need all of that space. If you have to come back in a race to make the line shorter or to extend it, just do it later. Just make sure the bar is on the same level as that equality. So you have the low t squared plus 5, that's the denominator. Then we take the derivative, that's the d, of the high, that's the numerator, minus the high, that would be the numerator, times the d, that's the derivative, of the denominator, that's the low. There we go. And that's all over the low squared. Now notice when I put that squared denominator. See how I put it directly underneath that minus. That way you can think of it like it's a seesaw and it's balanced. Now we go back and we simplify this. So you get t squared plus 5. Now the derivative of 3t squared. As a quick little trick. You ever need, not really a trick, more like combining two rules. To find the derivative of a constant times x to the n, notice the result is to take the constant out and then take the derivative of x to the n, which is n, the power, x, the base, and you reduce the power by 1. Notice the end result is that you take the constant times the power. Let's just do that. So the derivative of 3t squared is 3 times 2, that's 6. Keep the t, reduce the power by 1. You then have minus the derivative of 1, which is 0. Notice I'm now starting to drop using the derivative operator. I'm not writing it all down anymore. You then have minus a 3t squared minus 1, and then the derivative of t squared, which is 2t, and then you have the derivative of 5, which is 0. That's the numerator, and that's all over. You have a t squared plus 5 squared. That's the derivative, except we wouldn't leave it this way. We wouldn't leave it this way because there's common factors in the numerator, so I would write this as 2t times. Now take the 2t out of the first product. You'd get a 3 times t squared plus 5. Then you have minus. Factoring out the 2t out of the second product gives you a 3t squared minus 1. Notice I did not lose the parentheses because the minus is still distributed through that particular set of parentheses. And that's all over a t squared plus 5, that quantity squared. That then is equal to, you get a 2t, and then just going and multiplying this all out, you'd have a 3t squared minus a 3t squared. That would then give you no t squares. You'd have 3 times 5, that's 15, minus a minus 1, that's 16. So you get 16, and that's all over your t squared plus 5, that quantity squared. That would then give you your final answer, which unfortunately I'm running out of room. This would then be equal to, you get 32t divided by t squared plus 5, that thing squared. There you go. That would be the derivative. That's the derivative of y in terms of t. Mathematics is a language. You see, we have to teach you that language so that you are able to read these symbols later on in life when you take more advanced math classes or just look at your physics book. So, suppose you have a function that is differentiable, but you are only given this table of values. I want to know the derivative of the function u in terms of x and then evaluate it at -2. Well, to do that, I first need to know what the derivative of u is in terms of x. That is the same as taking the derivative of x squared over f of x as x changes. That requires a quotient rule. So I would have the denominator, the derivative of the numerator minus the numerator times the derivative of the denominator. And that's all over the denominator squared. There you go. Now we'll just come back and simplify that. That's then the same as writing. So we have f of x, and that's multiplied by the derivative of x squared, which is 2x. Notice the set of parentheses in this case means a multiplication between this object and this number. You then have minus x squared, and the derivative of f in terms of x is just f prime of x. And that's all over f of x, that quantity squared. Well, that first product is a little strange. So a lot of times people will just reorder it to put the constant, then the monomial, then the function. That way you don't have that problem with the extra set of parentheses being confusing. Then minus x squared, f prime of x, and that's all over the function value squared. So let's find out what the derivative of that u is in terms of x when we evaluate where x is -2. Everywhere you see an x, just plug in -2. So you get 2 times -2 times f of -2 minus -2 squared times f prime of -2. And that's all over f of negative 2, this expression squared. So let's see. In order to save a little bit of time, that's the same as writing in the numerator. You'd have a negative 4, 2 times negative 2. F of negative 2, though, that's just 1. Minus negative 2 squared, that's 4. And then I have f prime of negative 2. So f prime of negative 2, that's 2. And that's all over f of negative 2, that was 1. And I'm squaring it. So the end answer then is negative 4 minus 8. That would then be minus 12. That's the answer. That would then be the derivative of the u in terms of x when x is negative 2. So if you have a first derivative, you probably should guess that we have a second. After all, when you find the derivative, it's just applied to a function. But the derivative itself is a function. So you can take the derivative of that. So we need notation for that. So we'll write f double prime to mean the derivative of the derivative. We just need better notation, or at least to put down some rules. So the second derivative of f can be written any of these ways. Notice the double prime notation, the derivative of the first derivative, the second derivative, and notice the 2 is a power on the d and the dx because it literally means apply d over dx twice. You could also write dy prime over dx because that's the derivative of the first derivative. You could also write y double prime. In general, if you want, you can go up to third or fourth or fifth or sixth derivative. Just keep on cranking it out. In general, the nth derivative is not written with primes. You don't want to write n primes. So you write f with an n, but the n is parentheses. That means that many derivatives. It means you take the derivative of the nth minus 1 derivative. In Leibniz notation, you write d to the n of y over dx to the n. In terms of prime notation, you don't write y with a whole lot of primes. You write y with parentheses n inside. If you don't put the parentheses, it means power. Just as an example, if I gave you y is equal to x squared plus 3x, the first derivative then would be 2x plus 3. The second derivative would then be 2. And the third derivative would then be 0. And that's it. To recap, I've given you the derivative of sums and differences, constant multiples, products, and quotients. I gave you the derivative of a constant, x, x to a power, and also e to the x. Clearly, there's a lot more derivatives to go through. I also gave you a lot of examples of doing the derivatives, and I gave you a couple extra more interesting problems that you're going to see in your homework towards the middle end. So not just the crank out the derivative, but more notational fun or applications, finding a rate of change or finding a slope of a tangent line.